Hello guys, welcome to this YouTube channel. I'm starting a video series on linear algebra for engineers, and I'll be dividing this video series into four units: Unit 1, Unit 2, Unit 3, Unit 4. Unit 1 will be about the vector spaces, and Unit 2 will be about matrices. Unit 3 will be about the eigenvectors, and eigenvalues, and the Unit 4 will be about determinants. Now, to start with vector spaces, first of all, one should know Cartesian products and the binary operations. So these are the prerequisites. Cartesian products and binary. So this will be our plan. We'll start with Unit 1 and then Unit 2, Unit 3, Unit 4. And today's video is about the prerequisites, Cartesian product and the binary operation. Today we'll be doing this. So let's start with Cartesian product. So the reason why I'm starting with Cartesian product and binary operations is that because these will be very helpful in understanding the vector spaces. So to define this Cartesian product, suppose that there are two sets, given two sets A and B, both non-empty. Then we define A cross B, that is Cartesian product of A with B, like this. It's a set of all couples small a comma small b such that small a comes from capital A and small b belongs to capital B. And here we assume that A, B both are non-empty sets. And this symbol means is defined. So this means is defined. Now let's take a few examples of this. So take A equals to 1 comma 2 and B equals to 3 comma 4. Then A cross B is by definition the set of all couples such that the first entry comes from the first set and the second entry comes from the second. So let's make all these couples. First element has to come from A, second element has to come from B. So how many possibilities are there? Take one and three from here. So one from A, three from B. Now one from A and three from B. Two from A and three from B. Two from A and four from B. That's it. So A cross B has four elements here. So now let's take another example, slightly tricky one. So here, suppose A equals to 1 comma 2 and B equals to set of all x comma y such that x square plus y square equals to 1. And x, y are real numbers. So what does B represent? Well, don't you think that B represents a circle centered at the origin? So this is B, right? This is B. And what will be A cross B? Geometrically. Let's take a look at it geometrically. So first element has to come from A, that is 1, and second element has to come from B. So basically we are getting this. This one represents like 1 comma B and this one represents 2 comma B, right? So this is your geometric representation of A cross B in this case. Now if we take A equals to say 0 comma 1, closed interval 0 comma 1, and B equal to, as we took it earlier, as in example 2, then what is A cross B? So let's see. So this is 0 comma B, and here we have 1 comma B, and here we'll have say half comma B, right? So that way we're going to have circles here everywhere. And what does this give you? This gives you a cylinder, right? This is cylinder. Okay. So these are some of the examples of geometric representation of A cross B. And now if so, here's the result. If A has m elements, that is, if cardinality of set A is m, that is number of elements of set A is m, and number of elements of set B is n. Then number of elements of A cross B is mn. So this is one result that we're going to remember. Okay. Now in this definition, we assumed A and B to be non-empty. If either of A or B is empty, if either A or B is empty, then what is A cross B? Then it is defined as the empty set itself. Okay, so this is one result, and another result. How many subsets are there for A cross B? So the number of subsets of A cross B is 2 to the power mn, right? Okay. Now, note one thing. A cross B is not same as B cross A, right? So you can check this by taking examples. You can see it here itself in this example. A cross B is this, and B cross A is what? So we'll have 3 comma 1. We'll have 4 comma 1. We'll have 3 comma 2. We'll have 4. You can see that they are not same, right? So this is okay. We have checked this. Now let's take a look at the binary operation. Okay. So what are binary operations? So let's take a set and assume that it is non-empty. So we are taking a non-empty set. Now, what do we mean by binary operations on it? Let's see. So a binary operation on A is simply a function. It is if you take a function from A cross A to A, then you call that function a binary operation on. That's it. This is how simple binary operation is. Now, why is it required? Let's see. So suppose that you have a set. Let's call it S1. What are the elements of this set? Let's see. So you have, for example, a dog. You have a dog in this set. Dog. You have a cat. And let's say you have a fox. Now, on the other hand, you take this set and this set of all natural numbers, that is 1, 2, 3, 4, 5, 6, and so on. Now, you know that in this case, n, you can combine two elements. For example, take 2 and 3, you can add them, and this will give you 5. That is, you're able to add two elements of n to produce a third element 5, which is inside n. So can I say that addition is basically a function from n cross n to n, because it is taking 2 and 3 and converting it into 5. How? By adding them, right? So using binary operations, you can combine two elements of that set and produce a new element in the same set. So let's take a note of this thing. That is binary operation on set A gives us a way to combine two elements of A to produce an element inside A, right? So that is binary operation is doing. It is allowing us to combine two elements to produce another element inside the same set. Like here, if we talk about addition, so addition can combine two elements of n to produce a third element which still lies inside n. If we talk about multiplication, then again we can take any two elements and multiply to produce an element which still lies inside n. For example, take 2 and 4. So what will happen to 2 and 4? So 2 and 4 by multiplication will become 2 times 4, that is 8. What about subtraction? So if you take subtraction, if you apply subtraction on say 2 comma 4, then what do you get? You get 2 minus 4, that is minus 2. But minus 2 is not inside n. So subtraction is not a binary operation on n, right? Now, as far as this set is concerned, S1, here, can we combine dog with cat somehow? Can we combine cat with fox somehow? We can't, because we don't have any binary operation yet, right? So can we combine dog, and cat. In S1, answer is no, because we don't have a binary operation yet. Because we don't have a binary operation on S1 yet, right? Now, let's define a binary operation. What is binary operation? It is basically a function from like this, right? We have to define a function from S1 cross S1 to S1. Now, how many elements are there in S1 cross S1? Well, S1 has three elements, so 3, 3, 9. So there are 9 elements. So let's list out all those elements and try to define a function. So we can have dog cat is dog dog, or for simplicity, let's just take only two elements here. So we are writing all the elements of S1 cross S1. Dog dog, dog cat, cat cat, and cat dog. So this is our S1 cross S. We have to define a function from this to S1. So let's define a function. So here we have S1 cross S1, and here we'll write S1 elements. So here we have say dog, and here we have cat. This is the first element. Second element. This is the third element, and this is the fourth element. Let's define a function. So we can connect this to this. We can connect this to this, and this to this. So this is giving us a function, right? Now we're able to combine two elements of S1 to produce another element inside S1. How? What is that function? Let's call this function F. Now, what is F of cat with cat? Well, cat is going to cat. So we get a cat, right? So F is a function from S1 cross S1 to S1. Therefore, F is a binary operation on S1. Okay. So now let's let's take a look at some stats which we are going to use again and again in future. So, um, so this is the script n, and it is the set of all natural numbers 1, 2, 3, 4, 5, 6, 7, 8, and so on. Then we have jet, the set of all integers. So 0, plus minus 1, minus 2, plus minus 3, and so on. Q, script Q, is the set of all rational numbers. So it's the set of all the rational numbers. All right. And R, script R is the set of all the real numbers. All right. Now there are many types of binary operation. So some of them are as follows. Commutative. Okay, before this, let's note a few notations of binary operations. Okay, so suppose f is a function. This means that f is a binary operation on A. Now, we usually denote binary operation by star. So usually we denote functions by f, but when we're talking about binary operations, we use the symbol star. So here we use symbol asterisk to represent a binary operation. Usually we use this symbol star. That is one thing. Okay, so what is the meaning of star is a binary operation on A? It means that star is a function from A cross A to A, a function. That is means. Okay, that is one thing. Another thing is that so star is a function. Let's say we're talking about star of A comma A, right? We usually denote this by A star A. Okay. So like f of x comma y is now being denoted something like this. So this is the conventional notation. So we should denote star of A comma A prime like this. But this is being denoted using this. Okay. So that was about the notations. Now let's take some more examples of binary operations. How about is addition on script n a binary operation? So, what do you think should be the answer to this? Well, it means that we're looking at this function addition. What is it doing? Well, it is taking an element from n cross n, that is this couple, and sending it to A plus. So this is what addition function is doing. So we can denote this addition by say like this also. So what is plus of A comma B is A plus B, right? But you know that if A and B are both natural numbers, then A plus B is also a natural number. So yes, it is a binary operation. Yes. But what about the subtraction? Is subtraction a binary operation on script n? Well, the answer to this is no, because if you look at subtraction, then this is not even a function, because look at 2 comma 4. What is negative of 2 comma 4? I mean, what is the subtraction? Subtraction seen as a function. Yeah. What is this? This is 2 minus 4 and this is minus 2, which is not inside n. So this function is not sending this to the codomain. It's not even a function, right? So no. But similarly, division is not a binary operation on script n. Okay. Now let's move on to the types of binary operation. So there are various types, and we'll discuss only two of them. So one is commutative binary operation. What is commutative binary operation? So if star is a binary operation on A, or a binary operation star on A is said to be commutative if for every AB in A star B is same as B star A. This is what we mean by commutative binary operation. For example, addition, addition on set of natural numbers. But subtraction is not an example. Like multiplication is also an example. And what would be a known example? Subtraction. Subtraction on set of all integers, right? You can see that this is not a commutative binary operation because 2 minus 4 is not same as 4 minus 2. So this is commutative binary operation. And then we have associative binary operation. So star on A is set to be associative if for every A, B, C in A, bracketing doesn't matter. Bracketing doesn't matter. What I mean by this is the following. So if you want to combine ABC with this binary operation, then you can combine B and C first and then combine the result with A, or you can combine A and B first and then combine the remainder with C and you get the same thing. That is what associativity property means. So binary operation is said to be associative if this condition is satisfied. What would be an example? Well, an example would be addition, of course. Addition on and multiplication is also an example. Multiplication and what could be a known example? Subtraction. Subtraction would be a known example. Now, how many binary operations are possible on a set? So let's take a note of this result. This is our result number 3. So suppose that the cardinality of A is m, that is number of elements of set A is m, then the number of binary operations on A is, well, this is equal to the number of functions from A cross A to A. A cross A has m square elements. A has m elements. So number of functions from this to this would be what? This raised to the power m square, right? So m to the power square, m to the power m square. Okay. Now let's take a note of one definition. identity of a binary operation. Again, our notations are same as before. That is, star is a binary operation on set A. Then, if there exists, this symbol means there exists an element E inside A such that for every A in A star E equal to E star A equal to A. Then E is called an identity of A. Right? Example. So take Z and binary operation take plus. So the so an identity of addition. What will be the identity of addition on Z? 0, right? Because if you take any element from Z, say A, then A plus 0 is same as 0 plus A equal to A, right? For every A inside Z. Therefore, 0 is an identity of Z. Now, a question, does addition have any identity? Addition on script n, the set of natural numbers. What do you think will be the answer? Well, for starters, script n doesn't have 0 in it. So it may not have an identity. But let's prove it. So suppose on the contrary that E is an identity, right? Then what should be E plus 1? E plus 1 should be equal to 1 and E plus, right? E plus 1 should be equal to 1. But if you solve it, you get equal to 0. But 0 is not inside n, right? And that's a contradiction. Okay. So the answer is no. Now let's solve a few more problems. So consider this binary operation on Z defined as A star B equal to AB plus B. Now, is this star commutative? Is star associative? Uh, let's see. So, for commutativity, we should have A star B equal to B star A for every A, B, Z. So, take A equal to 2 and B equal to 1. Let's see what happens. 2 star 1 should be equal to AB plus B. That is 2 into 1 plus 1, and this gives us 3. And what is 1 star 2? 1 star 2 is 1 into 2 plus 2, and this gives us 4. So they are not equal, right? And therefore, answer is no. No. How about associativity? Let's see. So let's calculate A star, B star, C. What do we get? We get A star. What is B star C? BC plus C. So BC plus C. BC plus C. And how do we open this? Well, AB plus B. So A into BC plus C plus BC plus C. And this gives us ABC plus AC plus BC plus C. Now calculate this. A star B, star C, and see if you're getting this or not. That is this expression or not. And tell me in the comments. Okay. Now, another question is, say E is an identity of star on A. So it's an identity. And let's say E dash is also an identity of star on A. Then what is the relation between E and E prime? Relation between E and E prime. What do you think should be the relation? What if I told you that they're same? Let's see how. So since E is an identity, then by definition, E star E prime should be equal to E equal to this. This is just definition of identity. See, A star E equal to E star A equal to A, right? So I'm doing the same thing here. E star E dash should be E dash equal to E dash star E. Now E dash is an identity. So E dash star E should be E equal to E star E dash. Now if you but this guy is same as E dash. This is equal to E dash, that is equal to E dash, right? So they are equal. That means if an identity of a binary operation on a set exists, then it is unique. Therefore, instead of n, we'll be using the word the. So the identity of star on A instead of an identity of star on A. So I hope you understood today's lecture. So today we discussed the prerequisites for vector spaces, that is Cartesian product and binary operations. And in our next class, we'll be discussing the vector spaces in complete detail. So thank you so much for watching this video. Please like, share, and subscribe to this channel. Please also share it with your close friends so that they can also learn all these concepts from the scratch. Thank you. Bye bye. Have a great day.